नमस्कार, बेहद स्वागत है आप सभी का CIET NCERT के आज के इस खास कार्यक्रम में। मैं हूं तन्वी खुराना। इस वक्त आप हमें देख रहे हैं चैनल नंबर ई-विद्या, चैनल नंबर 9 से लेकर चैनल नंबर 12 तक। चैनल 9, चैनल 10, चैनल 11, चैनल 12। आप चाहें तो किसी भी चैनल पर इस वक्त हमारा ये कार्यक्रम देख सकते हैं। बेहद खास कार्यक्रम है वेबिनार सीरीज लिसनिंग टू लर्न, जिसे हम कहेंगे सुने और सीखें। और ये कार्यक्रम डिपार्टमेंट ऑफ एजुकेशन इन साइंस एंड मैथमेटिक्स NCERT के द्वारा कोऑर्डिनेट किया गया है। दिस प्रोग्राम इज द नेशनल स्टूडेंट आउटरीच प्रोग्राम दैट इज प्रवासी भारतीय एकेडमिक एंड साइंटिफिक रिसर्च संपर्क। दिस प्रोग्राम इंटीग्रेट्स इंडियन डायस्पोरा विद इट्स मदरलैंड। और आज जिस विषय पर हम बातचीत करने वाले हैं वो एक बेहद खास प्रोग्राम है, क्योंकि जो इसरो के मिशंस हैं आज की तारीख में वो सिर्फ इंडिया के लिए ही नहीं, पूरे वर्ल्ड के लिए इम्पॉर्टेंट है, स्पेस के लिए इम्पॉर्टेंट है। इसीलिए हम आज लेकर आए हैं आपके लिए एक विषय जो कि है सूर्य की ओर, इसरो का आदित्य L1 मिशन। Reaching for the Sun, the Aditya L1 mission of ISRO. This is our topic and we have a speaker with us. He'll be giving us the details regarding the Aditya L1 mission. अगर आपके पास कोई सवाल है, कुछ पूछना चाहते हैं, कुछ जानना चाहते हैं तो आप हमें फ़ोन कर सकते हैं। नंबर है 8800440559। अगर आप ईमेल के माध्यम से अपने सवाल हम तक पहुंचाना चाहें तो dth.class12@ciet.nic.in इस ईमेल आईडी पर अपने सवाल पहुंचा सकते हैं। इसके अलावा आप हमें इस वक्त देख रहे हैं हमारे यूट्यूब चैनल के माध्यम से, जो कि है NCERT ऑफिशियल। उसके लाइव चैट बॉक्स में भी आप अपने सवाल लिखकर हम तक पहुंचा सकते हैं। हमारे मेहमान को बेहद खुशी होगी आपके सभी सवालों का जवाब देने पर। ये हमारे इस प्रोग्राम का 60th सेशन है, यानी कि सत्र नंबर 60। और आज ये कार्यक्रम बेहद खास है क्योंकि एक इम्पॉर्टेंट टॉपिक डिस्कस होने वाला है। अगर आपके पास कोई ऐसा टॉपिक है जो आप सजेस्ट करना चाहें, आप चाहें कि हम इस प्रोग्राम में उसे शामिल करें, तो आप अपने सजेशंस, अपने एडवाइसेस, अपने फीडबैक्स भी हम तक पहुंचा सकते हैं। Let me tell you that in this particular program we have done so many topics. We have covered so many topics, be it IVF, be it Mumbai Dabbawalas, be it battery manufacturing, or be it the forgotten legacy of Aryabhat. So there have been a variety of topics that we have covered so far. So we would love to take your suggestions for sure. No matter where you are placed in this world, all you need is an internet connection and you can connect with us. You can even participate in this program. So we have a guest with us. Let me just tell you that he is Dr. Durgesh Tripathi. He'll be talking about our topic in detail, and so for bringing him here, we have a very important person, and he is the host, he is the coordinator of this entire program. Let me please introduce you to him, and he is Dr. Gagan Gupta. Sir, a very warm welcome to you.
Namaskar. Namaskar, Tanvi ji.
Sir is the brain behind this program. He is from Department of Science and Mathematics, NCERT, and he'll be introducing the topic. He'll be introducing our guest for all of you. And before we begin this program, before we begin the discussion, let me just tell you that we are extremely proud of the fact that India assumed G20 presidency and would convene the G20 Leaders Summit for the first time in the country this year, that is 2023. A nation deeply committed to democracy and multilateralism, India's G20 presidency would be a watershed moment in her history, as it seeks to play an important role by finding global pragmatic solutions for the well-being of all, and in doing so, manifest its true spirit of Vasudhaiva Kutumbakam, or should I say the world is one family. Vasudhaiva Kutumbakam also translates to one earth, one family, one future, and that is exactly the theme of this year's India's G20 presidency. So let me hand over our program to Dr. Gagan Gupta and request him to, sir, please introduce our guest, Dr. Durgesh Tripathi, to all our viewers. Sir.
नमस्कार दोस्तों, सादर प्रणाम। आज 60वें सत्र में हम लोग से एक बार मिल रहे हैं और आज का सेशन हमारे लिए बड़ा इम्पोर्टेंट है। दोस्तों, आप ये समय चल रहा है जुलाई और अगस्त का महीना। जुलाई के अगस्त हमारे इंडियन स्पेस रिसर्च ऑर्गेनाइजेशन और स्पेस रिसर्च के लिए बहुत इंपॉर्टेंट है। 14 जुलाई को हमने अपना चंद्रयान 3 लॉन्च किया, जो कि और उम्मीद है कि 23 अगस्त को शाम को 5:47 पर चंद्रयान का रोवर चंद्रमा की साउथ पोल पर पहुंच जाएगा। हम सब की शुभकामनाएं हैं, हम सब उस अवसर को देख रहे हैं। लेकिन इसी बीच में हमारे स्पेस साइंटिस्ट और दूसरे सेंटर्स के साइंटिस्ट ने सूर्य का मिशन को भी साथ में लिया और हमारा सैटेलाइट इस श्रीहरिकोटा पहुंच चुका है, जिसका कि प्रक्षेपण सितंबर के पहले हफ्ते में माना जा रहा है कि सितंबर के पहले हफ्ते में वो प्रक्षेपण भी हो जाएगा। और आज उसी L1 उस मिशन के सूर्य को समझने के लिए, सूर्य की कोरोना को करेक्टरिस्टिक्स को समझने के लिए आज हमारे साथ मेरे साथी डॉक्टर दुर्गेश त्रिपाठी फ्रॉम आयुका इंटर यूनिवर्सिटी सेंटर फॉर एस्ट्रोफिजिक्स एंड एस्ट्रोनॉमी पुणे से हमारे साथ हैं। दोस्तों ये आज का जो सेशन है एक क्रम में है। आपको मैं याद दिलाऊं कि इसके 60 सेशन सारे अभी तक के 59 सेशन सारे के सारे सेशंस हमारे NCERT की वेबसाइट पर हैं, जिसका कि एड्रेस आपको मालूम है और www.ncert.nic.in/webinarseries.php, जिसको कि आप हमारी स्क्रीन पर भी देख रहे हैं। और इसी क्रम में मेरी साथी तन्वी ने अभी बताया कि किस तरह के सेशंस को हमने लिया है और स्पेस रिसर्च से जुड़े हुए विषयों पर हमने पहले भी बात की है। आपको याद दिलाना चाहता हूँ 16 नवंबर 2021 को हमारे साथ अनिल भारद्वाज फ्रॉम फिजिकल रिसर्च लेबोरेटरी से जुड़े थे और उन्होंने इंडियन प्लेनेटरी मिशंस के ऊपर हमें बताया था। इसके साथ ही इसके बाद में 7 जनवरी 2022 को हमारे साथ डॉक्टर अरविंद रानाडे जुड़े थे, जिन्होंने कि हमें इंपॉर्टेंस एंड नीड ऑफ मिशन आदित्य के बारे में बताया था। दोस्तों आपको याद होगा कि एरोसेट मिशन आदित्य का पहला सेट हमारे पास 2015 सितंबर 28 2015 में हमने लॉन्च किया था, जिसने कि समझा था सूर्य के करेक्टरिस्टिक्स को। और उसके बाद में 17 मार्च 2022 को हमारे साथ दीपक मिश्रा, जो कि अहमदाबाद से हमारे साथ जुड़े थे, उन्होंने इस सब हमें इंडियन स्पेस प्रोग्राम एंड ओवरव्यू के बारे में चर्चा की थी। इसी के साथ में मोर रिसेंटली जनवरी 2023 में हमारे पास 6 जनवरी 2023 को इंडियन इंस्टीट्यूट ऑफ स्पेस साइंस एंड टेक्नोलॉजी IIST त्रिवेंद्रम से हमारे साथ जुड़े थे डॉक्टर आनंद नारायणन, जिन्होंने कि हमें जेम्स वेब स्पेस टेलीस्कोप के बारे में बताया था और उन्होंने हमें समझाया था कि किस तरह से जेम्स वेब टेलीस्कोप L2 पर है। ये L1 L2 आज इसके बारे में हम बहुत डिटेल से जानेंगे। बहुत ही संक्षेप में ये दो ऐसे L1 L2 L3 L4 L5 ऐसे पॉइंट्स हैं जहाँ पर कि किसी भी सिस्टम में किसी छोटे ऑब्जेक्ट को अगर रखें तो वो उसकी पोजीशन अपने दोनों मासेस के साथ बनी रहती है। आप आगे जाके पढ़ेंगे, ये बेसिकली एक 3 बॉडी प्रॉब्लम है जिसके बारे में कि हम आगे क्लासिकल मैकेनिक्स में बहुत और अच्छी तरह से पढ़ेंगे। कोई बात नहीं दोस्तों, अब मैं अपने साथी डॉक्टर दुर्गेश त्रिपाठी के साथ मुलाकात कराना चाहता हूँ। डॉक्टर त्रिपाठी जो कि इंटर यूनिवर्सिटी सेंटर फॉर एस्ट्रोफिजिक्स एंड एस्ट्रोनॉमी में पुणे में है और डॉक्टर त्रिपाठी इज करेंटली ए प्रोफेसर दैट इज साइंटिस्ट जी एट दैट सेंटर इन पुणे. He is also the principal investigator of the Solar Ultraviolet Imaging Telescope, which is also known as SUIT, which is on board the Aditya L1 mission, the first space observatory of the Indian Space Research Organization dedicated to solar observations. आज इसके बारे में हम बहुत डिटेल से जानेंगे. He is an affiliate faculty at the Center of Excellence in Space Science India, that is CESSI, at the Indian Institute of Science Education and Research, ISRO, Kolkata. From 2014 till 2021, Professor Tripathi was the head of the Max Planck India partner group on the coupling and dynamics of the solar atmosphere. Professor Tripathi completed his PhD doctoral program from the Max Planck Institute for Solar System Research, Göttingen, in 2005. He then moved to the Department of Applied Mathematics and Theoretical Physics at University of Cambridge, England, for his postdoctoral research. He spent about 6 years before returning back to India and taking up a position at Inter University Center for Astronomy and Astrophysics, Pune. During his tenure at Cambridge, Dr. Tripathi was awarded a prestigious research fellowship from the Clare Hall. He has also held several positions abroad, such as visiting scientist at the High Altitude Observatory, United States of America, and visiting professorship at the Kyoto University, Japan in 2017. Dr. Tripathi was awarded by the Physical Research Laboratory PRL, Ahmedabad, with the famous Booty Foundation Award in Plasma Science and Technology. In 2013, The Romanian Academy of Science presented the Group Achievement Award in understanding the genesis and evolution of coronal mass ejections, popularly called CMEs, to Professor Tripathi and his colleagues. Professor Tripathi has more than 150 publications with more than 3,000 citations in his name. Very distinguished scientist. Currently, he is a member of the editorial board of the Proceedings of Royal Society A, which is dedicated to the Royal Astronomical Society techniques and instruments and frontiers in astronomy and space science. Moreover, Dr. Tripathi is a member of the Coronal Loops Workshop Steering Committee, a life member of the Astronomical Society of India and the International Astronomical Union IAU. Recently, he has been elected as a member of the Division Steering Committee on the Sun and Heliosphere of the IAU, International Astronomical Union. Welcome, Dr. Tripathi. We would have loved to have you here, but seeing his involvement with this L1 mission, he is too involved in this mission, so it was very difficult for him to visit Delhi. But anyway, nevertheless, Dr. Sahab, you are still with us. At geographical locations doesn't matter much nowadays. So welcome once again, Dr. Tripathi, and now it is now all yours. Thank you.
Namaskar. Good morning. Thank you, Dr. Gagan Gupta, and thank you, Tanviji, for introduction and inviting me to give this talk. It's a great opportunity. It provides a platform to reach many students, which is what we actually wish for while giving these kind of talks. So as Dr. Gupta introduced you, that this talk is going to be about the Aditya L1 mission. So on my first screen here, on the bottom left, you can see the satellite, which is going to be launched on the PSLV rocket of ISRO. And in the bottom middle, you see this image of the instrument. This is Solar Ultraviolet Imaging Telescope, which we built here at IUCAA, of course, in collaboration with multiple institutions within the country. And that is going to be put here on the spacecraft. That's what this one here is. And when it launched, we are looking forward to getting data which will unravel the mystery of the sun in further detail. Now, before I go in detail and telling you about what Aditya L1 mission is, I thought I'll give you some perspective that why do we want to do this at all, and then give you an idea that what Aditya L1 will bring to us. So here, as Dr. Gupta already said, that you have had a talk by Dr. Anand Narayanan on JWST. This is James Webb Solar Space Telescope. And I put an image here. What you see is in this image, there are many objects, and a lot of galaxies are here. And where do we live? We live in one of those galaxies. That's what we call Milky Way. And the top right, you see an image taken from Ladakh Leh of our Milky Way. And there are about 100 billion galaxies in total in our universe. And our sun is one of the 100 billion stars in our galaxy. And when you talk about stars, the sun is a very normal star, right? So if you look at all the stars in the Milky Way, which is your galaxy, sun turns out to be a rather boring star if you think from the perspective of other stars, their size and mass and so on. But sun is very important to us. And when you compare also that in terms of the galaxy and the various things going on in the galaxy, where do we live? And so at the bottom here, there's an artistic impression of what our Milky Way galaxy would be looking like in its full glory. Then, and if I have to point that where do we live, that place would be Pune, because I'm sitting here in Pune, so I just put Pune here. But you can point to Delhi, and at that scale, it doesn't really matter where you point your arrow to. So as you can see that from that perspective, we live really, really far away from the galactic center, and it's a much, much quieter place when you compare with other dynamics which is happening within the galaxy itself. But our star, which the sun, has its own family, and that family is all the planets. So you have the sun and all the planets shown in the orbit. They're not on a scale, of course. But you also have asteroids, you have comets, we have us, we have all the animals, birds, and ourselves. And the whole life just depends on what the sun does. So solar radiation and the sun is providing all the energy for the life to sustain. And therefore, though it is not so important or not so active from the whole galactic or universe perspective, but it is much, much important for us because that provides us life. And no matter what you do, you have to live in the environment provided by our sun. So here is an animation which is showing that there are a lot of radiation, a lot of particles which are coming all the time from the sun towards into the interplanetary medium. Then it's coming and hitting your Earth. Earth has a magnetized sphere, so Earth is a magnet. You have the magnetic field lines going from both sides. Sun's magnetic field is coming from the sun side, connecting with the Earth's magnetic field and dumping all these energetic particles into the atmosphere of the Earth and providing you these ring currents and so on and so forth. And also all the radiation you have, which all the way comes to you, the visible radiation comes to you, the high energy radiation gets absorbed because the Earth has its own atmosphere. So whatever you want to do, you have to do with the boundary condition that the sun is providing. The sun has all these radiation and particles coming all the time. And so you have to define your life based on what the sun is providing you. Now, sun's study has been very, very important historically, and in the past, people have looked at the sun's motion, planetary motions, and so on and so forth. But the modern studies for the sun, that we call solar physics, started by Galileo. And Galileo was one of the first one who pointed telescope at the sun and started looking at how the solar structure is, how does it evolve, rotate, and so on and so forth. So this is in this animation here. So what he did was he would project the sun on a piece of paper and draw whatever he could see for that day. And then he would do it consistently every day. And that is put together here, made an animation. What you see that the sun's disk is not clean. There are spots. And what you also see that the sun rotates on its axis. And you can also see that these structures, these sunspots, are aligned in a line which is tilted from the north-south line you would have. So there's a rotation axis, and there is a magnetic axis, and there is an angle to that. Galileo also pointed out that these sunspots, they evolve with time. So as you can see here, if you point to one of those sunspots, you see this going from one day to the next day, the structure evolves. Now, of course, we can do much better with our modern technology, and when we can observe sunspots on regular basis. And what we find in the left here is a full sun image as you would take from a telescope from ground. Of course, this is taken from the Solar and Heliospheric Observatory. And what you find that it has a lot of sunspots on its disk. On the right-hand side is just a zoomed-in image of one of those regions and shown. And what is done here is to just put the Earth to compare the size of the sunspots. And as you can see, that sunspots could be as large or even bigger than the size of the Earth itself. So radius of the Earth is 6,400, and the radius of sunspot could be as large as around 10,000 kilometers. So the scales are really, really large, and these structures are really, really large. But then, if you keep looking at the sun, let's say every day for multiple years, it turns out that these sunspots are not always there on the surface of the sun. So here, the left image is taken in 2001, and the right image is taken in 2005. In the left image, you see there are a lot of sunspots on the surface, and in the right image, you see that there are no sunspots. What happened to those sunspots? And we figured that sun had a cycle of producing these sunspots. And you can see that here, these images are taken at the interval of 5 years. But if you take it every day, you would see that the number of sunspots are increasing day by day. It reaches to a peak, and then it starts decreasing and comes down to a minimum level. And if you do that, and define that, can I count these sunspots and define where they will be located, then you define a coordinate system. Of course, to specify anything as a point, then you need to do a coordinate system. So for example, in 2D, you have XY plane, but in 3D, you have XYZ plane. So if you go to look at the sun, then you can define a coordinate in such a way that the center of the disk will be 0, the top will be plus 90 degree, minus 90 degree, and then the east here will be minus 90, and the west will be plus 90. Now, remember that for solar case, this side is called west, and when you talk about the Earth coordinate system, this side is called west, but this is just the nomenclature. And once you define this coordinate system, then you can keep looking at these, how are they evolving with the number, and then where do they appear on the disk of the sun, and as a physicist, you want to first characterize those. And what you want to do, and what you find is that if you just count the number of sunspots every day, and it has been done since very long time. Here it is shown from 1880, for example. As you can see, the number of sunspots are increasing, then decreasing, going to minimum, then increasing, decreasing, increasing, decreasing. And that increase and decrease happen over a period of about 11 years. Now, since you know the coordinate system, you can put them as if like you can identify at what location they are appearing. And if you put them like this, what you see that when the sunspots number start to increase, they appear at the higher latitude on the upper hemisphere and also in the lower hemisphere. That's the equator. This side is the upper hemisphere, this side is the lower hemisphere. And then with time, they migrate towards the equator on this side in both the hemisphere, and then it goes to the minimum. And then when it reaches minimum, there are almost no sunspots. Then they start appearing at high latitude. So that's the characteristic. And this top diagram is called the butterfly pattern, that the sun shows the number of sunspots and all that. Okay, now so that's the characteristic we know about sunspots, and that gives you an idea about the sun has a cycle. Then came Newton, and if you notice, the Newton was born in the same year when Galileo died, and that's Newton not only discovered gravity, and here is a picture of Newton showing an apple in our campus at IUCA. He did not only discover gravity, but he also did a lot of work on optics. And one of the techniques he developed was spectroscopy. And spectroscopy is nothing but looking at the light and then inferring the properties of the source from which the light is coming from. And that's all we have. When you look at the astrophysics, all you get is lights and particles. So if you look at the light from a star or from any object from the sky, you should be able to infer that what this object is made of and various other properties. And that's what you can do for sun also. And Fraunhofer did exactly that. And he looked at the spectra, the light coming, and he used a prism and a slit, and he dispersed the light. Of course, you get the 7 colors vibgured, but since he was using a slit, what he also saw, there were these dark lines appearing on top of this vibgure color. And what was realized that these lines are called Fraunhofer lines because he discovered them, but these lines were due to the fact that some of those photons or the sum of those lights which are coming from the sun, they were absorbed by some certain elements. Now, if you've done atomic physics to some extent, you know that not any element does not absorb or emit a random photon at a random frequency, but what photon it will take would have a very specific property. And based on that, then you can infer that since this frequency photon is missing, what element could that be? And if you do that, then you know that the light coming from that particular source, that element is absorbing that photon. That means in the atmosphere, that element should be there. And based on that, looking at these lines, about 20,000 lines have been identified in the spectra of the sun. Now, these 20,000 spectral lines, they belong to different elements of their different ionization states, and so on and so forth. Helium, if you have heard, helium is the second most abundant element in the universe, but it was first detected in solar spectrum. So now, looking at these lines, you know what the sun is made of. And all the elements you find on the Earth, they are present in the solar atmosphere. And that's why we call you the stellar material, right? We are all stellar material because all these composition matters. What else you can do is, using Planck's formula, if you look at the light coming from the star or from the sun, you plot the whole thing as a function of wavelength, then you can use that to identify or to infer the temperature. And what Planck said, that if for a given black body, the function or this curve is unique for a given temperature. So if you observe this data and fit that with a given Planck function, then you know what the temperature of the surface. And what we find that the sun's surface is about 6,000 degree Kelvin. What else you can do with the spectroscopy? At some point, George Hale was mesmerized by the sun and its atmosphere, and of course, various other astrophysical objects. And what he wanted to do was to look at the sun, doing a spectroscopy, trying to figure out what these gases could be, what other structures are present. And he serendipitously, he put his slit, this slit here, to do a spectroscopy on a sunspot. And what he suddenly realized, that as soon as this slit goes to this sunspot region, he starts seeing the same spectral line started to split. And at the same time, Zeeman was a Dutch physicist. He was developing this quantum theory. And based on that, Hale could figure out that the sunspot regions are highly magnetic. And now you have a new addition to this, that in addition to all these lines you are observing and the gas and the temperature, you also now get inference that the sun's atmosphere is magnetic. Of course, he did it for a sunspot region, and what was found that these regions could be as large, having a magnetic field, as about 4,000 Gauss. When you compare to the Earth's magnetic field, is less than 1 Gauss. So you can imagine how strong magnetic field is. But now, if you do that on a regular basis, because the sun is close by, you can do the spectroscopy at each point on the sun, and you can measure magnetic field. So this is what is done here. In the left-hand side is just the sun's image taken in visible light. And the right-hand side is just at each point on the sun, you measure the magnetic field and put it as the point. So on the right side is called the magnetic field map, which is something called magnetogram, more technical word. But what it shows, like bright and dark patches. The bright ones, or the white ones, are the north pole of the magnetic field, and the black one is the south pole of the magnetic field. So this essentially gives you an idea that there is a huge amount of magnetic field on the sun's surface, and there is positive and negative polarity scattered all over on the sun's surface. With even modern techniques, what you could do now, as you do in high school experiments, you have a bar magnet and you draw a line of forces. Those lines of forces are going from positive to negative. A similar thing, a bit more advanced technique you can use to draw these lines of forces on the surface of the sun and see how these lines of forces are sort of oriented. And this is what is done for one of the few images taken from SOHO. And not all the lines of forces are drawn, only few to illustrate that you can see there are some of them, they are sort of open and they're going out into the interplanetary medium. And there are many of them which are closed, going from positive polarity to negative polarity. And if you draw almost all the lines of forces in the solar atmosphere, this is how the sun atmosphere will look like. So now what you have is on the surface, you have, and then there are a lot of magnetic field is spread on the surface, and these lines of forces are there in the solar atmosphere. You have all these closed fields. What you also see that if you look at the North Pole here and you look at the South Pole here, you have field lines which are seemingly open. Now, open magnetic field is not allowed because it violates the principle of del dot B equals to 0, which is the divergence free magnetic field is not possible. So the magnetic field has to connect. And what is understood is that these fields which are coming from the North Pole of the sun, they go all the way into the interplanetary medium and they come and connect to the South Pole. And these are the ones which are bringing a lot of particles into the Earth atmosphere, which I'll come to in a moment. Now, since our technology has improved, and this is an image taken in 2021. It's over a month time, and you can do it every day. And you can then look at the evolution of this magnetic field, which is on the surface of the sun. And what is shown here is that all these white and black are the magnetic poles. You see that there are two regions where you have mostly the stronger ones. So the stronger the magnetic field, the brighter the patch is in the North Pole. And the darker is the region, the stronger in the magnetic field in the South Pole. So there are two directions of the magnetic field. So you see there are two belts where they're appearing most of the time. But you also have a lot of these bright and dark stuff, which is spread on the surface of the sun. It looked like a pizza, you know, that you have the salt and pepper you put in, and you see these things are happening. Now, if you do it consistently for about 11 years, and you saw that the sunspots are showing 11-year cycle, this magnetic field is also showing 11-year cycle. And no wonder, because most of the magnetic fields are coming within the sunspot region. And if you do the magnetic field mapping, these things will be belonging to the strong sunspots, and whereas these ones are not related to sunspots. And if you do it for 11 years, what you find that at some point, when you have a lot of sunspots, you have a stronger magnetic field region here. And then when you go towards, then at some point, there won't be any sunspot, and therefore the magnetic field will be very, very tiny, if at all. And it comes back to its own glory again after about 11 years. So that essentially tells you that cycle as well. Now, the similar thing you can do, define the coordinates, and now measure magnetic field and all that. And what you find is this. So while you have this butterfly pattern in the number of sunspots and where they're located, you can do, if you do the same thing with the magnetic field maps, what you find is that, let's say 1980 is here, so sun has a sort of going towards maximum. But before that, the pole here is blue, which is a negative polarity, and this pole, North Pole, is yellow, which is a positive polarity. And you can see that about 10 years, this has changed completely from blue to yellow and yellow to blue. So the polarity of the poles of the sun had changed in 10 years. and then it comes back again after another 11, 10 years to back to blue here and back to blue here. And what you also see that when these magnetic fields are appearing in two sort of polarity, blue and yellow is positive and blue is negative here, you see that the blue is migrating towards the equator in the north, and the yellow and the blue in the south, the blue is migrating towards the equator. They're canceling out, whereas these ones are going towards the pole, and this yellow is going towards the pole in the south. So the whole dynamic pattern of the magnetic field just plays the role in changing the polarity of the sun. And this is 11-year cycle, this is 22, because a cycle is defined when you come back to the same thing, and here happens on 22 years. Now, this is all you can do from ground. You don't need to go to space. And what we know is that when sun is there and when you have the total solar eclipse, what happens in the total solar eclipse, moon comes and blocks the sun, and you start seeing this glorious outer atmosphere of the sun, which appears like this, right? So that's an image taken in 2008, I think, in the solar eclipse. And here is the moon. You can see the structures on the moon, which is blocking the sun. And what you see is these structures which are opening out into the interplanetary medium. And you have these structures which are showing closure, but they're also going all the way into the interplanetary medium. And because of these kind of observations, this happened in 1869. People wanted to do a spectroscopy of the atmosphere of the sun and trying to understand what the atmosphere is essentially made of. And in 1869, there were two scientists, Harkness and Young. They wanted to do this. They wanted to study what are the gases there. And then they started looking at spectra. What they identified that in a position to or in the Fraunhofer spectrum, when you looked at the absorption lines in the atmosphere here, they started looking at the emission line. So the photon is now emitted, not absorbed by an element. And what they found, there was a peculiar line, or that means that some photons were emitted at a peculiar frequency. And they didn't know what it was. Later on, it took about 60 years to figure out what that photon corresponded to. And it appeared that those ones would be because of the presence of highly ionized iron in the atmosphere. Okay, and it would be about 13 times ionized. That means you take iron element and it has 26 electrons. You take 13 electrons out of their orbit. So that will give you iron 13 plus. So it's 13 times positively ionized. And the amount of energy you would need to do this would be very, very large. And it will be as large as possibly equivalent to more than 1 million degree hot plasma. So the gases we are talking about here in the outer atmosphere, it has to be 1 million degree or more hot to produce these kind of photons. Otherwise, it won't be possible. Now, what makes this gas to be more than 1 million degrees? And that is also against principle of our understanding, in the sense that when you are going away from a hot body, you should be feeling colder. But here, you are feeling it otherwise. And the reason is that a while ago, I told you that the surface of the sun is about 6,000 degrees, whereas now I'm saying that this region, which is further away from the sun, is about 1 million degrees. And that is one of the open questions people are trying to figure out, that what could that be? And due to these high temperatures, the sun produces all these high energy radiation, which is extreme ultraviolet, X-rays, and so on and so forth. And that is why we need to go to space because these radiation, they are absorbed by our atmosphere of the Earth, and that is good. That's how we could live. Otherwise, if this radiation was coming to the Earth, we wouldn't survive. So to understand in the full glory that we need to go to space and try to understand what the sun is doing. And if you go to space and take an image of the sun in X-ray, then this is how the sun would look like. This is the one if you take it from ground or from space in visible light. And this is under the same time we take a picture of the sun in X-ray. And you can see that these regions, which are the sunspots, and they are the really highly magnetic regions, they are producing the most amount of X-ray in the atmosphere. If you do that over 11 years, that you keep taking image in X-ray, what you find that when you have a lot of magnetic field, you have a lot of X-rays, and when you have little tiny amount of magnetic field, you have very tiny amount of X-ray. So now you know that the whole radiation or the atmosphere is coupled in a way that the magnetic field is playing a very, very dominant and important role from the sun. Now, we know that there is an electromagnetic spectrum which goes all the way from gamma rays to radio. And we know that from the sun, we receive radiation all the way from X-ray to IR and radio. And this is 0 kilometers. So beyond this, it comes to us at the Earth. And that's why you see light outside. But beyond this here, it all gets absorbed in the upper atmosphere of the Earth, because you have ionosphere, you have mesosphere, you have stratosphere, and so on. So that gets absorbed. Now, these gases, when they absorb, they do a lot of dynamic phenomena they create in the atmosphere of the Earth. Now we have observatories, for example, from NASA. It's a solar dynamics observatory. It can observe the sun at various different frequencies. And this is what your ground, orange ball observation. But then when you detect different kind of photons and images in ultraviolet and near ultraviolet, that will essentially correspond to different kind of temperatures. So here we are going up to 15 million degrees. This is 6.3 million degree. This is 2.5 million degree, and so on. And this image is taken at 5,000 degrees. And you can see that the sun has very different phases depending on what kind of photon or what kind of temperature you're observing. Now, what happens to these to the Earth atmosphere when these radiation from the sun is coming? The Earth atmosphere absorbs it, and the X-rays absorbs at this height, UV at this, and near UV, mid UV goes all the way to the stratosphere, and visible and IR comes to us, and that's why we see light, right? What happens is, like, when these radiations, they are absorbed by the atmosphere, you can see that during the solar minimum, when you have almost no magnetic field on the surface, the temperature in the Earth is lower, which is about 600. And when it goes to the maximum, when you have a lot of magnetic field, that means a lot of X-ray, the temperature goes up to about 1200. So 400 Kelvin increase, and Earth's atmosphere is gaseous. So you heat it up, then it expands and then shrinks, and expands and shrinks. Now imagine you put a satellite there. The satellite will face a lot of drag forces, and the satellite will start wobbling. And if it is a symmetric satellite, then it will start doing like this. So all your communication, which you are dependent on because of all your mobile phones and televisions, they will have all the problems. So that's a space weather effect, which we have to deal with because the sun's radiation we cannot control. Now, the sun also has particles. So if you're sitting on the Earth, you have to face all this, which is coming from the sun, along with the magnetic field. You have the radiation, you have the particles. Luckily, we have this magnetic field, which is deflecting all these particles, which is coming from the sun, right? You can see these are getting deflected, and you are going into the sea of these particles. They are deflected away, and that is why your atmosphere is very, very important. See, the Earth's magnetic field just stops, and when it stops, sometimes the sun's magnetic field gets into direct contact with the Earth's magnetic field, and then that's the time when it can put a lot of energetic particles. And those energetic particles are highly charged, so they can go towards your electric pipeline because they want conductors, and they go through the transformers, and these particles could be keV, MeV, and your transformers are only in volts, so they cannot handle those particles and they fuse. So you have electric power blackouts. So that's another space weather effect. This is just to show that when the radiation and particles are coming, how actually they are hitting into the Earth's atmosphere. This I showed earlier, but again, just to reinforce when they're coming, these particles and radiation they absorb, and sometimes you see this got connected with the magnetic field of the sun, of the Earth, and then it brings down on towards the day side, and then the particles go inside the atmosphere. And it produces aurora, which you can see if you go to northern countries such as Scandinavia and so on, and you see these lights, and they are produced by the sun particles getting into the atmosphere. They are ionizing nitrogen, and nitrogen then emits green light, and that's what you see. So these are beautiful scenes. If you get to go to Norway, you all show this. All right. Now, because of all this importance, since 60s, there have been a number of space missions getting towards looking at the sun. And also there have been a lot of upgradation from the ground-based observatories looking at the sun all the time to understand what is this star about and what it does and how we can try to understand so that protect ourselves. In the left, here is an image taken from Swedish Solar Telescope, and these structures are about as large. This is in the surface of the sun. Now here on the top, this is taken from space, and there are 3 telescope data has been put together. There are 3 colors into this. These are ultraviolet, so there are no colors to ultraviolet. So these are the fake colors people put in just to visualize. And you see that the temperature there is about 20 to 30 million degrees when you have these kind of eruptions. So it's a sudden, intense brightening, and the energy could be as large as 10 to the power 32 Earths. And they produce a lot of energetic particles and a lot of radiation. And if it is directed towards the Earth, it could have a lot of electric power blackout, communication issues, and so on. We also see that there are a lot of dynamic phenomena happening in the atmosphere of the sun. So this is an animation made based on the data taken from Japanese satellite Hinode, and this is only a part of the sun. So that's the disk, and you have we call them as a limb, and here it is looking into the atmosphere. You see a lot of material is going up and coming down. You have all these structures just sitting there and wobbling, and what we're trying to understand is what are the physics involved which can explain these phenomena. Why this thing is going up and coming down? It's like a projectile motion. You're throwing a ball and then this comes back here. But there's nobody throwing a ball. So what exactly is happening there? Can we understand it based on our basic understanding of how the gas and magnetic field has an interplay, and try to explain these structures? Then you have even larger scale eruptions. So this is something called prominence, which is sitting there for months, and then one fine day it just decides to erupt and gives you these intense brightening as flares. And if all these mass is coming into the interplanetary medium, and I put here the size of the Earth just to show that how big in this comparison to this is. The good thing is that the space is vast. These structures, they expand like anything while they travel into the interplanetary medium. And then you have these, when you block the sun, you start seeing all these eruptions and mass ejections coming out of the sun. And one of these mass ejections could be as large as about 10 to 15 kilogram of the plasma. Okay. And these, they also change with a time scale of 11 years, which is the solar cycle. If I just put in here again to re-emphasize that these kind of eruptions during solar minimum, during this time when you have less magnetic field, less X-ray, you also have less eruption. So one eruption in a day or two, whereas during the maximum, you could have 10 of these coming all the time. So depending on when do you want to launch a satellite with an astronaut, you can define that, the solar activity as minimum. So the eruption is going to be so much, but if it is a maximum, you try to avoid because the eruption is going to be so many, and there is always a better probability of you being hit by such a storm. And when these CMEs, they come in, they disrupt the whole magnetosphere of the Earth, if you like. So this is the Earth. The sun's wind is blowing from the left side and producing all this ring current. Depending on what the magnetic field of the ejecta is, it's just getting combined with Earth's magnetic field and producing aurorae, and they could also produce navigation signal disruption, electric power blackouts, and so on. So what have we learned from all this? We learned that the sun and its atmosphere directly affect our life, mainly due to our dependence on technology. Right? Of course, our life is dependent on the solar energy, but that visible energy is coming in. But our dependency is getting more and more on the sun because of the technology. The atmosphere is so dynamic that the structures in the atmosphere change on a time scale of few minutes to hours. And it is the nearest star where we can study its evolution on the fundamental scale. You can resolve sky sizes which are like few tens of kilometers and try to understand that how does that feature evolve and try to pin down the basic physical principles in those structures. And we understand this, we can extrapolate our knowledge from the sun to other astrophysical objects. Now, based on all this, there are number of things we have understood. We have developed a tremendous understanding of our own star, but there are many things which are unknown. There are many known unknowns, and there are many unknown unknowns. And that's what we hope that we will be discovering more and more in the future, that what we still don't know that we don't know. So what have we learned? That the sun has electromagnetic radiation. It has long-term effect like satellite drag, oxygen, ozone chemistry in the Earth atmosphere, because that photons in the ultraviolet, they come into the stratosphere. In stratosphere, you have ozone and oxygen, and they absorb these photons and they get dissociated or photoionized, and that changes the whole chemistry of ozone and oxygen. So what we want to understand is that how does the electromagnetic radiation, mostly in ultraviolet and X-ray, originate, and how does it evolve and vary with time. Then in addition to that, you have the solar wind, which is a continuous ejection of plasma from the sun with magnetic field and charged particles. They also create aurorae, they create space weather. Now, they also have sudden large-scale eruptions with the magnetic field and so on. And what we essentially want to understand that origin of these large-scale eruptions and charge properties. So where we want to go from here, we want to create an observatory which provides a long-term uninterrupted observation of the sun. And for that, to get into the full glory, we need to go to space. And that is why we have this Aditya L1 mission of ISRO. It is going to be at 1.5 kilometers away from Earth towards Sun. So between Sun and Earth, there are any two bodies. You have 5 positions where the force of gravity balances each other. So if you go to L1, so if let's say consider this is Earth, this is Sun. If you go to L1, that is where the force of gravity is balanced. L2, there also the force of gravity is balanced. L3 is also force of gravity balanced, and so is for L4 and L5. If you go to L1, then when the Earth moves, then L1 will also move. So if you put a satellite there, it will keep observing the sun all the time. So Earth is moving, L1 is moving, so the observatory is moving, and it will provide continuous observation of the sun 24/7. If you go to L2, then you will block the sun's light because of the Earth, and then you start looking at the night sky, and that's what James Webb Telescope is doing. And there are other possibilities and pros and cons of going to L3 and L4, but Aditya L1 mission is going to be at L1 point, which is about 15 lakh kilometers away from the Earth towards the sun. It is going to carry 7 instruments on board, and that's the satellite, the way it will be launched. This is put on a trolley at the moment for various testing and so on, and hopefully it will be launched in the first week of 2023. What it is going to carry 7 instruments And these are just the names, but it is going to look at visible light, it is going to look at the infrared light, it is going to create artificial eclipsing and look at the outer atmosphere of the sun, it is going to look at the X-ray radiation, it is going to look at ultraviolet radiation, plus it is going to detect those particles, catch those particles coming from the sun, measure their properties in situ and lead them away. And also, because how and where this ejecta, if it is going to be important for the geo effectiveness, depends on the magnetic field of the sun. We also have a magnetometer which will measure at that point what the direction of the magnetic field is, and therefore can give a pre-warning that there is an ejecta coming with such and such property, and you got to be careful. And it will be launched on PSLV XL. So what will happen is that you will take rounds around the Earth. So you few flybys, and then after it has reached a certain height, then you give a slingshot, and it will travel for about 112 days and reach at a point. So 112 days and 15 lakh kilometer, and it will reach this location where then it will be inserted into the L1 orbit, and it will be orbiting around the L1 and keep looking at the sun all the time. Right. So I showed that there are a number of observatories already, but Aditya has uniqueness. The uniqueness is that it is going to observe all across the electromagnetic radiation, starting from hard X-ray and to the infrared from the same platform. It would have a direct measurement of the magnetic field in the solar corona. It is going to image the entire disk in the near ultraviolet, which has never been done before, and it is going to help us address that how much role the solar UV radiation plays in terms of ozone and oxygen chemistry and measuring interplanetary magnetic field. So with that, I come to the end of my talk, and here I just put in some pictures of the satellite, which was released last week by ISRO. So this is the packed version of the satellite. Here there are different telescopes. This is the coronagraph. That is the ultraviolet imager. The coronagraph is just creating artificial eclipsing. It is going into the thermovac chamber where you do a lot of heating and cooling cycles so that you do various tests for the spacecraft and so on. Here is hanging, just showing some other tests. And here is one of the payloads. This one here is Solar Ultraviolet Imaging Telescope, which we built at IUCA in collaboration with ISRO, ISRO Kolkata, IIA, and other PRL and other institutions in the country. Thank you very much. I'll be happy to take any questions.
So thank you very much. बिल्कुल प्रोफेसर त्रिपाठी, आपको सुनने में इतना मज़ा आ रहा था कि मैं तो भूल ही गया कि घड़ी आगे निकल चुकी है. We have many questions with us, but we are very short of time. Now I am afraid that we can take the questions, but viewers, you can send your questions to us, and we will definitely get back to you with the answers of your questions. Some questions which you have received we will be answering in consultation with Professor Tripathi. Really, I enjoyed a lot, Professor Tripathi. We like to hear you again on this platform, but just for a small information once again, that you talked about the magnetic reversals which took place around every 10 years or 11 years on the sun. We are going to have a session again on the magnetic reversals on the planet Earth, in January 2024. Probably it takes nearly a million year or so, something.
Yeah, something like that.
Something like that on the surface of the Earth. So it will take. We are going to have a session on January 2024. On magnetic reversals on the planet Earth. Well, colleagues, thank you very much, Dr. Tripathi. We look forward meeting you again on this platform, more about this L1 mission after it is being launched. Dear friends, Tanvi.
Yes, sir. Let me thank Dr. Tripathi, for being with us today, and it was wonderful having you, sir. This was a very important session, and because it was in a series, so I would request all the viewers to watch the earlier sessions that we have done in this same series, and the upcoming sessions also we will be letting you know all the details, that when are they going to come, what are the topics, each and everything. So please watch the webinar series, and the link we have already shared it with you. Well, apart from that, if there are any suggestions, of course, you're more than welcome. So, we have one very important information as well. So, I would request, sir, to pass it on to you. So,
Yes, the next session is due on September 8th. This is on space situational awareness, current and future scenario. Dr. A.K. Anil Kumar from ISRO Telemetry Tracking and Command Network, that's ISTRAC. I know that all of you know about what ISTRAC is now, because it has been in newspapers so much. So looking forward meeting you on September 8th on this platform. I want to have one more announcement regarding this, that ISRO is offering a workshop during October on this issue of the space situational awareness and space traffic management, that is SSA and STM. All children and faculty members are invited to participate in this workshop. They can the email, the address, the link has been given here in jigyasa.iirs.gov.in/SSA. So please register yourself for this program. This is a very important program of ISRO, and we are going to meet Dr. Anil Kumar, who will be talking about prevent collisions in space, and then manage it, and how to manage space debris, and of course how to make career in space sector. Thank you very much, friends, for joining us. Looking forward to meeting you again on September 8th.
thank you. Thank you so much, sir, for this information. And I really think that all the interested people who are watching this program, they'll be definitely registering for this workshop. Thank you so much, Dr. Tripathi, for being with us today. It was wonderful having you. Your presentation said a lot about the Aditya L1 mission, and also about the sun, things that most of the people didn't know about till now. So thank you so much for being with us. It was a pleasure.
Thank you very much. It was a pleasure talking to you and to the audience.
Thank you. Thank you. Thank you to Dr. Gagan Gupta as well for being a wonderful host as always. Thank you so much, sir.
Thank you, Tanviji.
Thank you. Thank you to all the viewers for being a part of this program, and every time we try and come up with a very new topic, and which is exciting, which adds to your knowledge. So this is a great program for all the children, for each and every person, for the entire Indian diaspora who is staying away from their motherland. We are wrapping up this particular program, but we have a lot more sessions for all of you on different subjects, on different topics throughout the day. Our upcoming session is at 12 o'clock, so please watch that for sure. And regarding the NCERT textbooks, if you have not purchased the textbooks till now, please purchase them. There are multiple options. Either you can go to the sales counter and buy those books, or you can simply download the PDF version from NCERT Diksha or ePathshala website or their mobile applications. And the third medium is you can simply place an order through our website. The website is ncertbooks.ncert.gov.in. So thank you so much once again for being a wonderful viewers. And yes, I'm Tanvi Khurana. I'll take a leave of you. Have a good day ahead. Namaskar.
बीच में